All right, hello everyone, and welcome to Unit 4, Lesson 3, which is on representation of reactions. Today's understanding is that a substance that changes its properties or that changes into a different substance can be represented by chemical equations. Your objective is to represent a given chemical reaction or physical process with a consistent particulate model. And the essential knowledge is that balanced chemical equations in their various forms can be translated into symbolic particulate representations. When representing reactions with particulate models, there are a few key ideas that we have to keep in mind. First of all is the conservation of matter. That means that the same number of each type of atom must appear before and after the reaction. And that just goes back to atoms can't be created or destroyed. Same with the law of conservation of mass. The law of conservation of charge means that the total charge stays the same throughout the process. And we also have to look at our stoichiometric ratios, where the number of the reactant and product particles match the coefficients in the balanced chemical equation. And then when we're looking at phase representation, just remember that when you have a solid, it's going to be shown as a tightly packed sample. Liquids are going to be still close but randomly arranged. Gases are going to be widely spaced and kind of sporadic. And then aqueous ions are shown as free ions surrounded by water molecules or whatever solvent you're working with. And then the diagram on the right is just a representation that shows the idea of using methane reacting with oxygen to form carbon dioxide and water. And you can see that each particle model matches the balanced chemical equation, which is a very important part of this lesson. One of the most common applications of using particulate representations of physical processes is with phase changes. So if we were to look at the phase change from solid water to liquid water, before we're going to have those water molecules arranged in a fixed ordered lattice, which is the ice or the solid version of water. And then afterward, when it is converted into a liquid, those water molecules move a little bit more freely while remaining still in close contact. So as you can see here in the diagram, the left would be the before and the right would be the after. And then here you can see the phase changes from solid, liquid, and gas. And I wanted to give you this information so you did know all of the different phase changes and their names. Now let's look at a chemical process with a precipitation reaction, which is what we learned about last lesson. Before the reaction, we have both our ionic compounds, silver nitrate and sodium chloride. They are dissolved in water, so their ions are free and moving around separately. And remember, we know that they are soluble in water because silver nitrate has nitrate in it, which is part of our solubility rule, and sodium chloride has sodium in it, which is part of our solubility rule. So we know both of these are ionic compounds that are soluble in water. So when we look at them at the particle level, both of them are going to dissociate into ions, which we can see here in our two beakers of our dissolved ionic solids. After the reaction takes place and those two solutions are mixed together, silver ions are going to combine with our chloride ions to form our solid precipitate, which is AgCl. That AgCl is going to settle at the bottom of the container because it is a solid and is more dense. The sodium and the nitrate ions do not change. They're going to remain in the solution as spectator ions. And essentially, this particle diagram is just going to show us how only certain ions are participating in forming the solid. and how the spectator ions are just remaining in solution. So particulate level representations act as a visual translation of balanced chemical equations. So they help us connect what we can see, like color change, gas bubbles, or solid formation, to what's happening at the particle level, where atoms and ions are rearranging according to the law of conservation of mass and conservation of charge. So when we are balancing equations, remember you are only changing the coefficients, which are the large numbers to the left of your substances. You are not changing the subscripts. If you are changing the subscripts, which are the small numbers, like in SO2, that means you're changing the identity of that substance. So you are only changing coefficients, which are the large number to the left of the substances. If you see an odd and an even number of atoms, you need to go to the odd atom, that substance, and multiply it by 2 in order to get it to an even number. Also, another hint is to keep your polyatomic ions together if at all possible. It's going to make it easier in the end. And then always double check your work and make sure everything is balanced on both the reactant and the product side. All right, so this one says to balance the equations and include your states of matter for the reactants and the products. I actually have the balancing for these equations on the next slide, so we're just going to make sure that we have the correct substances with their states of matter, and then we will balance them on the next slide. So first, let's look at this double replacement reaction for number 1. We need to figure out if we have any precipitates formed, and we can do that by figuring out which of these substances are soluble in water. So remember, our solubility rule is SNAP. So we have sodium nitrate, ammonium, and potassium. If one of those 4 things are in our ionic compounds, we can assume that it is soluble. If one of those 4 things are not, then we can assume it is not soluble. So we have sodium in sodium phosphate, which means that is going to be an aqueous solution because it is soluble in water. Silver nitrate has nitrate, which means it's also soluble in water. Silver phosphate does not have one of our 4 soluble ions in it, so that is going to be our solid or insoluble. And then sodium nitrate has 2 of our substances from the rule of solubility, so it is definitely soluble in water, so that would be aqueous. Then looking at number 2, the combustion of ethane. So if we have a hydrocarbon, C2H6, ethane is a gas, and we are combusting it. We know in order to combust something, we need oxygen, so we're going to have O2 gas as our other reactant. And then we know when we have combustion reactions, we are forming carbon dioxide, which is another gas, and water, which is a liquid. So now let's move on to the next slide to balance these equations. All right, so first we have our double replacement reaction. So we have 3 sodiums and 1 sodium, so I'm going to multiply this by 3. I have 1 phosphate and 1 phosphate. I have 1 silver and 3 silver, so I need to multiply this by 3. And then my equation is balanced. Then moving on to number 2, whenever I have a combustion reaction, I always start with the odd oxygen because as you can see in the reactant side, I can only have even oxygens. So I'm going to go right to this water molecule and see that I have 2 hydrogens and 6 hydrogens, which means I would have to multiply this by 3 to get that to 6. but that is going to keep this odd oxygen odd. So in order to get rid of that, instead of multiplying this by 3, I'm going to do the next multiple of that, which would be 6. So now this oxygen, there are 6 of them, so it's an even number. And now I need to balance those hydrogens. So I now have 12 hydrogens on the right, which means I need to multiply this by 2. Now my carbons on the left are 4, which means I need to multiply this carbon dioxide by 4. And now total number of oxygens on the right side, I have 4 times 2, which is 8, and 6 times 1, which is 6. So 8 plus 6 is going to be 14, which means I'd have to multiply this by 7 to get 14. Then number 3, again, I go right to that odd oxygen. So I have an odd number of oxygens over here, so I need to multiply this by 2, which means I need to multiply SO2 by 2 as well, so the sulfurs even out. And now I have 2 sulfurs. I have 2 times 2 is 4, plus 2 is 6, and I have 2 times 3 is 6. So this is now balanced. And then for our last practice problem, we again have an odd and an even oxygen, so I need to multiply the odd oxygen by 2. And now I have a total of 6 oxygens on the left, so I need to multiply this oxygen by 3 to get that to 6 oxygens on the right. Now I have 2 potassiums, which means I need to multiply this by 2, and now I have a balanced chemical equation. All right, I hope this lesson was helpful to you. If you have any questions, please feel free to reach out. Have a wonderful day.